Today I want to, all right, so today I want to go over quantum field theory again, and today we're going to be deriving the Klein Gordon equation. So derivation, this is the derivation of the Klein Gordon equation. And for organizational purposes, what we're going to find in quantum field theory is that we want to keep a couple of important equations in mind. We have the Schrödinger equation. So we have Schrödinger. Schrödinger. We have the Schrödinger equation. All right. We have the Klein Gordon equation. Klein Gordon equation. These are all equations of motion. The Dirac equation. The Dirac equation. And the Proca equation. All right. The Klein Gordon equation applies to spin zero particles. Spin zero particles. The Dirac equation applies to spin 1/2 particles. Spin 1/2 particles. And the Proca equation is spin 1 particles. And we'll talk about what that means later. The Schrödinger equation applies to, this is quantum mechanics, not quantum field theory. But these are the big equations of motion that spark our interest when we're studying quantum field theory. And I do this kind of stuff. I do this kind of stuff so that you can remember it easier. Because what I find is that if I can bunch things in, if I can bunch topics into specific modes of thinking where I have these important equations of motion, I can remember them better. If I remember, okay, I have these types of equations that they're essential. I put this in my bin of essential equations. I remember them better. I remember what they mean better as well. And so what we're going to be going over is this one, the Klein Gordon equation. The Klein Gordon equation is a relativistic version of the Schrödinger equation. So this one sort of evolves into this one. Okay, when we begin to consider particles that have zero mass. Okay, which like photons, and photons are things that travel at the speed of light. Okay, and our big stipulation here, or our big step that we're going to use to make this transition, is redefining our energy to be E squared equals, actually I'll do it like this. So our relativistic notion of energy is the square root of m squared e to the 4th plus p squared c squared. All right. This is the relativistic equation for energy, and E equals mc squared is non-relativistic. So let's begin with the Schrödinger equation. The Schrödinger equation looks a little something like this, where we have p squared over 2m plus our velocity, not the velocity, sorry, the potential, which is denoted v. So this is a potential, not a velocity, times phi is equal to the energy times phi again, where this is the operator, this is the eigenvalue of our operator, and these are the eigenstates of our operator. Remember, the eigenstates are the things that remain the same when we operate on them. Okay? And we're just scaling them up by some number. Okay? All right, well, what I can do here is let's square root both sides here. I'm going to square root both sides here, like that. Okay, and so now I can start plugging things in. So I'm going to use this here as the template for developing a new equation given this Schrodinger equation. Okay, so this is the Schrodinger equation. Schrodinger equation, and we're going to evolve into a Klein Gordon equation where we consider this energy and not this energy. All right, so we have E squared. The E squared part turns into, well, we need to remember our operators in quantum mechanics. So this is EI dt squared. Okay, this inside of the square here is the operator associated to energy. Okay, our total energy here. And our momentum operator, our momentum squared, is h bar over I times the gradient squared. So this is the operator associated with momentum. So what we can do now is we can develop this equation where we have I h bar dt squared acting on phi. Okay, now we have this side of the equation. Here's this side of the equation, and that turns into this here. I will bring this up here for a second. We have E. So I have this right here. So this is this. All right, I'm jumping around here a little bit. So this E squared is this, plugging it into here. Then we have this mc to the 4, m squared c to the 4, phi. And then we have this momentum squared c squared here. Momentum squared is this. So we have h over I squared times c squared times phi. So this is our relativistic energy in combination with our momenta, and our energy operators. So this arrow might be a little bit confusing. Okay. Because here we have E equals this, here we have E squared. Okay. And what I'm going to do now is I'm just going to divide, I'm going to square everything out, and I'll divide everything by c squared. So it's going to look like this, where we have negative 1 over c squared d squared dt squared phi equals, I'm going to rearrange this a little bit too, squared phi minus m squared c squared over h bar squared times phi. And this is from here to here is some basic algebra. This is something that you could do by yourself, okay, as a good practice. But really, I'm just dividing things out by h bar, getting rid of the i's by squaring them, and dividing things out by c. And we get this equation. Now, I'm going to bring this to this side here, and we'll be able to cancel out negatives. And what we get is 1 over c squared d dt squared minus, actually what I'll do here, this is good. This is good here. The Laplacian, this here is called the Laplacian, times phi is equal to m squared c squared over h bar squared times phi. All right, this here is the Klein Gordon equation, but I'm going to clean it up now. So this is good old Klein Gordon equation, but let's clean this up now. So to clean this up, I'm going to bring ourselves over here. This is the same thing as 1 over c squared times d dt, so the derivative with respect to t, minus the Laplacian squared, That's the operator operating on phi. Okay, and I'll just bring us back down here to see that. I'm just factoring out phi here. All right, and then we have m squared c squared over h bar squared. Okay, and times phi. So if we recall from quantum mechanics now, we have that the energy, actually I'll do it like this, if we have this operator, IH bar d dt. All right, for this IH bar d dt is associated with the energy. This is associated with the energy times phi. Okay, and h over I d dx, or this is also this thing right here, times phi is equal to the momentum times phi. So what we have here is we have an operator associated with a number, right? So this operator, IH bar d dt, is associated with our energy eigenvalue. We have h over I d dx, or more generally, I'll put in the derivative with respect to all locations in space, or all dimensions of space, is associated with our momentum, right? This is the operator, so this is the operator, and this is the eigenvalue of the operator. Right, and same thing here, operator with its eigenvalue. Now we have this operator. So from the Klein Gordon equation, this here is the Klein Gordon equation. This here is the Klein Gordon equation, and we have this operator now. We have 1 over c squared d dt squared minus this is akin to this here. Okay, which is m squared c squared over h bar squared, where this is the operator, this is the operator, and this is its eigenvalue. This is the eigenvalue, this is the operator, this is the eigenvalue. Okay, so what can we do here? We can clean this up even more, actually. All right, to really, really organize this in our heads and to really keep this in our minds, at the forefront of our minds, we could say d dt is associated with energy. d dx, or I keep on wanting to put d dx, but this here is associated with the momentum. This is the derivative with respect to all dimensions of space. And then when we combine the two, we have this d squared. I'm just taking all constants out. You could set c equal to 1 and h bar equal to 1. All right, we just get this d dt minus that squared. So when we square these things, these i's inevitably go away, and we have this m squared c squared. Well, actually, if c squared is equal to 1 in this case, and h bar is equal to 1, and this should be squared. If that's equal to 1, if these two things are equal to 1, we get m squared. So we have an operator associated with energy, an operator associated with the momentum, and an operator associated with the mass. Okay? This is the crux of the Klein Gordon equation. These are not part of the Klein Gordon equation. This is what we get. This is the something interesting that we get from the Klein Gordon equation. Okay? Where we have operators associated with given eigenvalues. And as a final touch, to make this more succinct, in quantum field theory, we say that this here, what I have written, is equal to this. All right. This here is the D'Alembert operator. All right. So we have sort of this Laplacian, we have this time derivative, and we have this D'Alembert. And that is it for this video on quantum field theory. Again, if you like these kind of videos and want to see more, you can head over to my Patreon page and you can request for me to do something. If you're interested in tutoring in physics, biology, or chemistry, you can go onto my website at tristancarmacy.com, and I can give you a good some good tutoring. And I hope you enjoyed this. I hope you got something out of this, and I'll see you in the next one.